Hi, welcome back. Today we're going to talk about the mean value theorem for integrals. So remember, back in our derivatives chapter, we talked about the mean value theorem for derivatives. And that was a theorem that basically said, if a function is defined on a closed interval and meets some continuity and differentiability requirements, then we're guaranteed at least one value of c somewhere in the interior of the interval where the average rate of change over the entire interval equals the instantaneous rate of change at x equals c. That was the mean value theorem for derivatives. Now, the mean value theorem for integrals is again talking about something of an average, but here it's talking about the average value. So before we can get into the specifics of the mean value theorem, let's talk about what it means to be an average value, the average value of a function. So think about it this way. Imagine we have a function, something like this, defined over some closed interval, from here, let's just say, from A to B, some closed interval from A to B. If you want to find the average value of the function, just think about it this way, like the average value would be, in some sense, if you took every y value, added them all up, and then divided by the number of y values you have. That function values are y values, but the trouble with that is that, well, technically speaking, there's an infinite number of values between a and b. If you think about real numbers, there's an infinite number. If you think about integers, of course, or there's not an infinite number. But if you think of even rational numbers, irrationals, and then real numbers, of course, there's an infinite number. But just bear with me. Let's think about this. So suppose you could just add up every one of the function values. In other words, you take f of c sub 1, that's an x value. That's an x value. You take all of your x values, all infinite number of them, you evaluate them at f, so you find the y values. So there's an infinite number of values in that expression. You add them up, and you divide by the number n, whatever n is. Okay? Well, if we can rewrite that using sigma notation, that's the sum of f of c sub 1 plus f of c sub 2 plus f of c sub 3 plus f of c sub 4 dot 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 up to f of c sub n. That's the sum from I equal 1 of f of c sub I. Now, hopefully, that looks a little familiar to you, hopefully. And then maybe you see where we're going to go with this, because what happens perhaps if we strategically multiply by b minus a over itself? We just multiply by 1, of course, but we did that. Now, of course, b minus a over b minus a, that's a constant, and let's factor out the b minus a on the denominator and leave the b minus a on the numerator. In the same sense, let's take 1 over n and factor it inside. Now, why can we do that? Because 1 over n is a constant as far as the summation is concerned. It's not indexed, so we can treat it like a constant. What that does for us is it gives us b minus a over n times that summation. Basically, the b minus a over n, sorry, I said that wrong. It's b minus a over n inside the summation, so it's times the f of c sub I. But what do we know b minus a over n is? That was our definition for delta x when we were talking about a Riemann sum. Okay, so that's delta x, and now this is exactly our definition of a Riemann sum. Only difference is now we have this 1 over b minus a out front. Now, of course, a Riemann sum, if it's finite, is not equivalent to a definite integral. It's an approximation of a definite integral if you have a finite value of m. However, if we have if we take the limit as n goes to infinity of this expression, we take the limit of this expression as n goes to infinity, well, we get the limit of a Riemann sum, which we know is exactly equal to this definite integral. The only difference now is there's a 1 over b minus a out front. So it turns out, if you want to find the average value of a function, you simply evaluate the definite integral over the interval of interest, and then you multiply by 1 over b minus a, where a and b are the endpoints left and right hand side of the interval of interest. That will give you the average value, the average y value of a function, the average height of a function. Okay? And there we have our formal definition here in definition 4.71. The average value of a function over a closed interval a to b is given by 1 over b minus a times the definite integral from a to b of f of x dx. So, super easy to do this. Here, let's take a look. So if you want the average value, so let's just say average value of this function, it's going to be equal to 1 over b minus a. So remember, that's always a, and that's always b. A is always the left side, b is always the right side. So 1 over b minus a will be 1 over 2 minus negative 1. So be careful with your negative signs. Times the definite integral from negative 1 to 2, from a to b, of f of x dx. So x squared plus 1 dx. So it's just an integral with a fraction up front. In this case, what's the fraction? It's 1 over 2 plus 1, so there's a 1/3 out front. So we have 1/3 times the definite integral from 1 to 2 of x squared plus 1 dx. And this calculation will give us the average value. Now, of course, that's just a definite integral now, and there's nothing really crazy about that definite integral. We can just use the power rule, and we're done. So let's see. 1/3. Now, what's the antiderivative of x squared plus 1? It's x cubed over 3 plus the antiderivative of x, which is just, of 1, which is just x. And then we're going to evaluate at -1 and at 2. We need to apply the fundamental theorem part 2. So what does this give us? This gives us a 1/3 out front. I'm going to open some brackets since we do have multiple terms here. We need to be careful when applying the fundamental theorem part 2. So let's first evaluate capital F of b. That's going to be 2 cubed over 3 plus 2, close parentheses, minus open parentheses. If we plug in a -1, be careful when we're cubing that -1. -1 cubed over 3 plus -1, close parenthesis, close bracket, equals 1/3. Now what do we have here? We have, 2 cubed is 8, so we have 8 over 3 plus 2 minus, okay, -1 cubed is -1, so -1 cubed, -1/3, plus the -1 would be -1, like so. Okay, at this point I'm just going to grab my handy-dandy calculator that works very well for just basic algebra, or this is basic arithmetic rather. So we have 8 over 3 plus 2, minus a -1/3, so that'd be plus 1/3, then minus a -1 would be plus 1. That gives us 6. So everything inside the brackets turns into a 6, and of course 6 now times 1/3 gives us a 2. So the average value of this function, the average height of this function, x squared plus 1 over the interval from 1 to 2, is 2. Just a quick picture of what we're talking about here. Now, of course, x squared plus 1 is just a standard parabola that's been shifted up 1 unit. So the vertex is here at 1, 0, and it looks something like this. Now, we're only concerned about the region from -1 to 2, however. So let me just draw the region from -1 to 2. Let's see here. Okay, from -1 to 2. So, if we plug in a -1, we get -1, 2. So we have this point like right here. So the parabola is going to start there on the left, and now we plug in a 2 where it stops on the right. We have 2 squared plus 1 is 5. So 1, 5, 1, 1, 2, 3, 4, 5, and the parabola stops over here somewhere. Okay, so we have the closed interval, the parabola, and that's the only portion of the parabola we're looking at. So what we're doing here is finding the average y value. And what we found is, well, the average y value is 2. So it's like right there. So if you can imagine taking the infinite number of points on that graph, only considering the y values, adding them up, and dividing by infinity, you would get 2. 2 is the average height, or the average y value. Average function value. Okay? Here's something else it does for you. Here's something that's kind of cool. It finds basically the height of a rectangle. Here, let me see about, let's see, 2 different colors here. So if you think about the definite integral, if you only consider the definite integral, it looks like this, right? That's what the definite integral has found as the net area. And since this function's non-negative, well, then we get just net area, that graph. Now here's what another way to think about the average value. The average value gives you a height such that you can form a rectangle where the rectangle that's green, and it's kind of disappearing here, the area of that rectangle is equal to the definite integral. So you have a definite integral here from -1 to 2. So this was -1 to 2. Okay, and so now we have that weird shape, which is the black, and then we have a rectangle with a height 2. But guess what? That is equal. The rectangle area is equal to the definite integral. Why? Because what's the area of this rectangle? The width is 3, right? Between 2 and -1 has a base, the width of 3, base of 3, and the height's 2. So the area of the rectangle is 6. What was the definite integral equal to? It was 6. Before I divided by 3, the 1/3 was out front. The definite integral was equal to 6. So the average value of the function, yes, it gives you the average height, the average value, but it also it does this curious thing where it allows us to find a rectangle, a single rectangle, where the area of that rectangle is equal to that weird shape definite integral. Again, the black shaded area, which is the underside of a parabola, the region between the underside of a parabola, 2 vertical lines on the x-axis, is a weird shape. But the definite integral, and this is non-negative, so the area of that weird shape is equal to the area of that green rectangle. Kind of a cool little geometric tidbit of information. Okay, let's look at another example real fast. Determine the average value of f of x equals 2x plus cosine x over that interval from -pi/2 to +pi/2. Okay, so again, all we have to do here is to find the average value. So the average value over AB is given by 1 over b minus a times the definite integral from a to b of f of x dx. That's all you gotta do. Basically, evaluate a definite integral and multiply by 1 over b minus a. So let's see what we have here. Average value equals, okay, 1. Oh, now be careful here with these, pi over 2s and -pi/2s. So it's, here is a is the left and b is the right. So we have pi over 2 minus a -pi/2 times the definite integral from -pi/2 to pi/2 of the integrand 2x plus cosine x dx. Okay, so what do we get? We get 1 over, what's pi/2 plus, it's double negative, so pi/2 plus pi/2. Well, we have basically 1/2 pi plus 1/2 pi, which is just a pi on the bottom. So we have 1 over pi times, now let's just go ahead and evaluate this definite integral. What's the antiderivative of 2x? Okay, power rule says it's x squared. What's the antiderivative of cosine x? Okay, well, our knowledge of trig tells us that antiderivative is sine x. So sine x. And the fundamental theorem part 2 says we need to evaluate at negative pi over 2 and pi over 2 and then solve. Okay, so let's see. We get, let's see, a 1 over pi out front. And then we need to apply the fundamental theorem. In fact, I'm going to use a bracket here since we have parentheses and all kinds of stuff going on here. Let's see. If you plug in a pi over 2, it's going to be pi over 2 squared plus sine of pi over 2. That's capital F of B. Minus, okay, now capital F of A would be negative pi over 2 squared plus sine of negative pi over 2, close parentheses, and close bracket. That's capital F of A. Okay, just some little bit of algebraic and trigonometric simplification here. So we have 1 over pi out front. Now let's see. Pi over 2 squared, that's just pi squared over 4. So pi squared over 4. What's sine of pi over 2? Well, unit circle, sine of pi over 2 is 1. So plus 1. Minus, okay, I dropped the parentheses around the first because there's no negative sign up front. So those are fine parentheses to drop. I didn't drop my second set of parentheses, again, because there's a negative sign in front. We have what? But pi over 2 in parentheses squared is positive pi over 2. Oh, sorry, positive pi squared over 4. Positive pi squared over 4. Negative times negative is positive. Now, what's sine of negative pi over 2? Now, negative pi over 2, that's the same thing as 3 pi over 2, which is negative 1. So we have that situation. Okay, so we have a 1 over pi out front, and then with brackets we have pi squared over 4 plus 1. I'm now going to distribute the negative. Then we have negative pi squared over 4 plus 1. Well, what do you see about those pi squareds over 4? There's a negative 1 and a positive 1. So they add to 0, leaving us with a 1 plus 1 is 2. So is 1 over pi times 2, which is 2 over pi. So that is the average value. Now, what is that approximate? I don't know. 2 divided by 3, I guess. And I don't know. About 0.66 or so. 2 divided by pi. Yeah, it's about 6.64 if you want to be approximate. Again, we prefer exact solutions, but if you just want to think about graphically, that's a y value, an average y value, an average function value of about 0.64. Okay, so here, I don't know that graph right off the top of my head, but we can pull up Desmos really fast, and Desmos will let us look at it and make sense of it. So give me just half a sec to load up Desmos. And so the function is what? 2x plus cosine x. Now we are only concerned about negative pi over 2 less than equal to x less than equal to pi over 2. Okay, so here we go. So if you look at the entire graph, that's what 2x plus cosine x looks like. It's like a kind of a wavy, if you think about the waviness of cosine with the rigidness of 2x, like a line with slope 2, you kind of get a wavy line type situation. But we're only interested in negative pi over 2 to pi over 2. So the average value, well, that's like the average y value, which we found was about 0.64. So y equals, well, let's type it in, 2 over pi, which is about 0.64. So that means if you can imagine, taking every one of these y values, negative 2.672, negative 1.979, there's an infinite number. Taking them all, adding them all up, and then dividing to get an average, the average would be 2 over pi. Okay? That is what the average value is doing. It's the average function value, the average height is the way I like to think about it, the average height of the function over this interval from negative pi over 2 to pi over 2. Okay? And then if you also want to think about it this way, if you think about a rectangle that goes between negative pi over 2 and pi over 2, so there's a rectangle if we shade below it, like so. Let's see here. Also, y is greater than or equal to 0. If we, oh, not capital Y. Y is greater than or equal to. If we do this, that rectangle is equal to the definite integral of the red function, that is the net area between the red function and the x-axis from negative pi over 2 to pi over 2. So here I can do this. I'll show you like a graphical representation of the integral here. I'm going to have to break it apart into two spots. So let's see. First, y is greater than 0. So there's the right-hand side, and now let me get the left-hand side. Let's do this, and then let's do this, and let's do this. And let's make them both red. Okay, so there's maybe a graphical representation of the definite integral of the original function, 2x plus cosine x. Now remember, that function is not non-negative. So this region, I'll change the color, the region below the x-axis that I just changed to blue, that is going to be counted in a negative fashion when we're calculating the definite integral. So in fact, the definite integral was what? Was 2. Okay, now why is it 2? Because basically the answer I got when I was doing the average value calculation was 2 times 1 over pi. The answer you get before you multiply by 1 over pi, that's the answer to the definite integral. So the definite integral here would be the region above the x-axis minus the area of the region below the x-axis, and you get 2. Which, by the way, there's a rectangle over the same interval from negative pi over 2 to positive pi over 2, and it also has the same, has the area that's equal to the definite integral. So here, the area of this rectangle is 2. Why? Well, think about it. The height is pi over 2. The width is pi. We're going from negative pi over 2 to positive pi over 2. So the width is pi. The height is 2 over pi. If you multiply 2 over pi times pi, you get 2. So the area of this blue rectangle is equal to this definite integral. Again, and where the definite integral is the area of the region above minus the area of the region below, the signed area, the net area. Okay? So basically, rectangle is equal to net area. So the purple rectangle here is equal to the net area of that region. Pretty cool. All right, in the next video, we'll talk about how the mean value theorem allows us to figure out the location of the average value. So in these two examples, we talked about how to find the average value. The mean value theorem takes it one step further and says, let's find the location of the average value, and it guarantees that the average value falls between A and B. Okay, that's for the next video. Any questions in the meantime, just let me know. I'll see you soon.